Chapter 4, Applications of Derivatives, 4.1, Extreme Values of Functions, Part 1. Your objective for this lesson is to find extreme values of functions. Okay, so starting off with our definition of absolute extreme values. Let f be a function with domain D. Then f of c is a, an absolute maximum value on D if and only if f of x is less than f of c for all x in D. In other words, the y value at c is bigger than all the y values on that graph in its domain. Or B, an absolute minimum on D if and only if f of x is greater than or equal to c for all x in D. So, in other words, every other y value is greater than or equal to the y value that you're looking at. That's an absolute min. Example 1. On the interval negative pi over 2, comma pi over 2 inclusive, f of x equals cosine x takes on a max value of 1 one time and a minimum value of 0 two times. So that is this arch right here. This is cosine x, so y equals cosine x. And the function g of x equals sine x, this is sine x, takes on a maximum value of 1 and a minimum value of -1. So you can see up here, we're at the highest point. This is at y equals 1. Down here, lowest point, y equals -1. And looking at cosine again, we see the maximum. This is at 0, 1. And the min, this is where y equals 0. And notice that there are two mins. They are the same number because y equals 0 at both these points, but 0 is the lowest y value on the graph for cosine. Example 2. Here we have the same graph 4 different times, but we're looking at different intervals of the graph. So in part A, we have y equals x squared, and the domain is from -infinity to infinity. So I've drawn some arrows on the ends of my graph here, indicating that it goes on forever in both directions. So in this case, the absolute max doesn't exist. So there is no absolute max. There is no maximum value bigger or y value bigger than every other value, because that's just going to keep going up forever and ever. I can't point to the top of the graph. The absolute minimum, however, I can see this side is going up. The y values are going towards positive infinity. Same over here. So my min is what I see right here. So that is the point 0, 0. Okay, and that occurs at x equals 0. So you might say it's at x equals 0, but the point is 0, 0. In part B, let me get the shade going here. Okay. In part B, where you have the same graph, y equals x squared, but we're looking on the inclusive interval 0 to 2. So between these two blue dots here that I've drawn onto the graph. In this case, there is an absolute max because this part of the graph doesn't exist anymore. Neither does this part. So that's gone. So my absolute max then is right here. That is the highest point on the graph. And that is the point 2, 4. The absolute minimum is down here. That is at 0, 0. Part C, still looking at y equals x squared, but now our domain, instead of being 0 to 2 inclusive, we are not including 0 anymore. So you see that open circle. Okay, this does not change the fact that the highest point on the graph is right here at 2, 4. However, before, when I had my minimum right here at 0, 0, there isn't a point at 0, 0 anymore. And since there are numbers existing on a continuum, I can't really point to the next smallest number. So in this case, there is no absolute minimum. Okay. Last part here. Part D. So now you see we've gone from 2 square brackets to 1 square bracket to both curved brackets. And as you may have guessed, right here, that's not the absolute max anymore because there's no point there. And just as before, there is no absolute minimum with that open circle. So open circles means that there's no absolute max or absolute min there. Okay. The extreme value theorem states that if f is continuous on a closed interval, so that's important, closed interval a comma b, then f has both a maximum value and a minimum value on the interval. Okay. So let's look at this here, some definitions for local extreme values. And this says, let C be an interior point of the domain of the function f. Then f of C is a local maximum value at C if and only if f of x is less than f of C for all x in some open interval containing C. So basically, your y value has to be clearly greater than other points in the interval, on the interval. Or B, a local minimum value at C if and only if f of x is greater than or equal to f of C for all x in some open interval containing C. So same thing, but with a min. You're looking for a lot of things that are clearly greater than your y value. Some other words that you might hear, instead of hearing local extrema, you may hear the term relative extrema. And instead of absolute extrema, you might hear global extrema. So local min or max, same as a relative min or max. Absolute min or max is the same as a global min or max. This is another theorem for you, the local extreme values, or talking about local extreme values rather. And it says that if a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime of C equals 0. And this is something that we've actually already used a few times to find maxes and mins, setting the derivative equal to 0. You already know that if you have like a curve like this, for instance, and I want to find that value, like the slope here is 0. That is a horizontal tangent line. So we've already used this a few times. Definition of a critical point. A critical point is a point in the interior of the domain of a function f, and at which f prime of 0 or f prime does not exist. So that is a critical point. Either a max or a min, or f prime doesn't exist. And that could happen if, for instance, I had a corner here. So I know that my right and left hand derivatives aren't going to be equal. That is not differentiable because it is a corner, but that would still be a critical point of my function. Example 3, find the absolute maximum and minimum values of f of x equals x to the 2/3 on the interval -2, 3. So these are our endpoints. And we're going to solve this two ways. So we're going to look at the graph of the function first. So we have x to the 2/3 power, not 5, 2/3 power, from -2 to 3. Okay, so looking at this graph here, it looks like, well, if I can trace at -2 up, I see my y is at 1.587, and at 3 it's a little higher, so it looks like my max is definitely at x is 3, and then my min is going to be, looks like at x equals 0. But let's do this analytically also, because you know you're not always going to have your calculator. So analytically, what I want to do is take the derivative of this function, and set it equal to 0. So f prime of x is 2/3 x to the -1/3, which I can rewrite as 2 over 3 times the cube root of x. Okay, and if I try to set this equal to 0, well, that's never going to happen, because I'm always going to have that 2 on the top, so I'm never going to have 0 divided by this denominator, so there are no zeros. But, so that's not going to happen. But I do see if x equals 0, then I'm going to have 2 divided by 3 cube root 0, which is 2 over 0, which does not exist. So since that's not defined there, I have a critical point at x equals 0. So this is a critical point. And now we're going to look at the values of f of x at the critical point and the endpoints. So evaluate f of x at critical points and endpoints. Okay, so my critical point was x equals 0, so I'm going to say f of 0 is 0 to the 2/3, which is 0. Okay, and then I want to say f of -2, because that was one of my endpoints, is -2 to the 2/3 power, which I can rewrite as the cube root of 4. Oh, maybe I should not skip that step. This would be -2 squared, and then the cube root of that, which is the cube root of 4. And f of 3 is 3 to the 2/3, which is the cube root of 3 squared, which is the cube root of 9. Okay, so looking at these, pulling up my calculator, let's evaluate them. So we have the cube root of 4 and the cube root of 9. So 1.587 and 2.080. Okay. And now looking at these values, I can see that this is the biggest and this is the smallest. So that tells me that I have my absolute max of 2.080, so approximately 2.080, or cube root of 9, at x equals 3, and my absolute min is equal to 0 at x equals 0. Okay, this was just looking for absolute max and min values. If I did want the local values also, then this point would be a local max. Because when we were looking at that graph, you did see it was higher than other points around it. It's just not the highest point on the graph, so this was the highest point on the graph. So that's the absolute max, the global max. Example 4. Find the extreme values of f of x equals 1 divided by the square root of 4 minus x squared. So again, let's start by solving this graphically. We have 1 divided by the square root of 4 minus x squared. Oh gosh. And let me change my window here. Maybe I need to zoom in more than that. There we go. Okay, so that's my graph. It looks like a U field goal or something here. And it looks like I have my min again at x equals 0. And if I trace, it says y is 0.5. So I would guess that that's my absolute min. And some maximums at around, going the wrong way, 2 and -2, around that neighborhood. Okay, well, let's do this analytically. Okay, analytically, we know that this this denominator cannot be equal to 0. But more than that, this is a square root function. You know that whatever has to go under the square root needs to be positive. So basically, 4 minus x squared needs to be greater than 0. And when we solve this, I change this to an equal sign. I would get x is plus or minus 2. And I like to do this with a number line to see where my values will fall. If I plugged in a 0 for this, so some test numbers, 0 is between -2 and 2, so 4 minus 0 squared is greater than 0 because 4 is greater than 0. So this would be good. If I plugged in a -3, we would get 4 minus -3 squared, which is 4 minus 9, which is not greater than 0, so that would be bad. And the same thing would happen with a +3. So I know that my numbers need to be between negative 2 and 2. Cannot be negative 2 or 2 because then that denominator would equal 0. We don't want that. And this all tells us that our function is defined on this domain. So negative 2 to 2. Open interval, not the closed interval. So since there are no endpoints, our extreme values have to occur at critical points. And the first thing I'm going to do to find those is find my derivative. So f prime of x equals, well, this is kind of hard. Let me rewrite this function. This is, remember, square root is the same thing as 1/2, and since it's in the denominator, I'm going to set it equal to 4 minus x squared to the negative 1/2. So that negative tells me that it was in the denominator of a fraction. So then now I can bring that negative 1/2 in front. 4 minus x squared to the negative 3/2 times derivative of the inside is negative 2. Negative 1/2 times negative 2 is just a 1. So I end up with 4 minus x squared to the negative 3/2. Oh gosh, sorry. That's not a negative 2, that's a negative 2x. Don't forget the x like I just did. So really we have a negative 1, a negative 1/2 times negative 2x, and we end up with 1x. You could also write this as x over 4 minus x squared to the 3/2. Okay. And to get this equal to 0, the numerator would have to be 0. So we'd have 0 over 4 minus 0 squared to the 3/2. And that part will go away. So we're just left with 0. Okay. This turns out to be the only critical point for this function because to get the denominator set equal to 0, we would have to plug in a 2 or a negative 2. Okay, so 4 minus 2 squared is 4 minus 4, that would be a 0, but we don't have those values included. We've already excluded them from the domain of our function. So this is our only critical point. And let's plug that back into f. So f of 0 is 1 over 4 minus 0 squared square root, okay, which is 1 over the square root of 4, which is 1/2. Okay. So we definitely have either a min or a max at 0, 1/2. Looking from the graph, it's obvious that this would be a min, and this is the absolute min. Okay. But if you were trying to figure out if that's a max or a min, just looking at this, you would want to plug in a couple numbers on either side and see what happens. So I would probably plug in like a 1 or something else, and you could see that that denominator is going to get smaller. So you're going to end up with bigger x values, bigger y values. So that's how you're going to figure out if this is a max or a min. Notice that there are no absolute maxes on this one, and that's okay because we were dealing with an open interval not a closed interval. So that can happen when you have an open interval. That wraps up 4.1 part 1.